In the last video, we discussed sparse vector representations and how to use them in Qdrant. In this video, I'm going to show how these representations could be used for keywords-based text retrieval in theory and in practice. I'm going to start with a lexical retrieval and then going to give a quick intro into the sparse neural retrieval, which combines the preciseness of keywords-based matches with the semantical understanding of machine learning models. And to start this journey, we need to understand firstly how to convert text to sparse representations. As you remember from the previous videos, each dimension in a sparse representation refers to a certain object. Which objects do text consist of? Well, of words. There are extremely many words out there. However, if we are working with a limited amount of texts in one corpus, we certainly can form a limited list of each and every unique word used in these texts. So, form a vocabulary. As you remember, words in vocabulary usually are ordered based on the letters in them, and that will come in handy. Let's say we have a dataset of a grocery shop item descriptions written in English. The words that we can use to describe produce should be limited, say to a couple of thousands of words. Imagine them from apple to zesty, ordered and enumerated based on this order. Now we could use this vocabulary to turn our grocery item descriptions into the sparse representations. For example, let's look at these two. To convert them to sparse representations, we'll have to take each word and find its corresponding index in our vocabulary. This index is going to be our index in the sparse representation. Let's turn grated hard cheese into a sparse vector. Let's say that in our vocabulary, cheese is 101st word, grated is 151st, and hard is 190th. Then our description could be represented as this sparse vector, once indicated that each word in this description is presented once. In the same manner, mac and cheese could be represented as this sparse vector, with the index 101 referring to the matching between this description's word cheese. If we would have a little longer descriptions where the words start repeating themselves, for example, 4 cheese pizza, 4 cheese lovers, then the value of the repeated term in the sparse representation will reflect how many times this word occurs in the encoded text. This value is usually referred in the field of informational retrieval as term frequency, or TF, term frequency of a word in the document. This way of representing text as sparse vectors is called bag of words model. Words are placed into the sparse representation as if in the bag, without minding their order, but minding their frequency in the text. If we can represent text as sparse vectors, we could also compare these texts, as we compared sparse representations in the previous videos. Then the text with a matching keyword, as grated hard cheese and mac and cheese, will have a non-zero similarity score. The higher the term frequency of a matched keyword, the higher the similarity score. This already hints the idea behind the keywords-based retrieval systems. We could encode all of our textual documents as sparse vectors and then measure their similarity to the query through the process of retrieval. Yet in retrieval, we care about the relevance between a document and a query. Of course, documents and queries with matching key terms certainly have some probability to be relevant, but it's different based on the keywords because some of them are more important than the others. Let's continue this build-up of our retrieval system based on our grocery shop item descriptions. In this system, most probably the words like tasty or fresh are going to be used pretty frequently to describe some produce. At the same time, specific key terms like mozzarella or gorgonzola are going to describe very few items, well, unless it's a cheese-specific Italian shop. So in this corpus, the keyword mozzarella is more important than the keyword tasty, just because it's more rare. A numerical way to describe this rarity, or to describe this importance, is called inverse document frequency, or IDF. Basically, it's a statistics calculated on the whole corpus, showing in how many documents this particular keyword is occurring. The rarer it does, the higher is the IDF of this keyword. Then we could update our bag of words document representations in our handmade retrieval system by scaling each word in each document with this word's importance in the whole corpora, or IDF. Then the similarity score between query and the document sparse representation made in such a way will take into the account each matching keyword's global importance. With these examples getting extremely cheesy, we got ourselves the first very basic model for keywords-based retrieval, which is called TF-IDF. To use it in practice, you would have to calculate inverse document frequency of each and every word in your corpus, which means running calculations on every document in it. In Qdrant, we decided that this is inconvenient and took the responsibility of calculating and updating IDF for you on our server side. For that, you will just have switch on IDF modifier when configuring a collection with sparse vectors, and then, once switched on, IDF will be updated and maintained on the collection level. That means that you won't have to calculate and add this IDF part to your sparse document representations. Qdrant will do it for you and apply the score directly per keyword when calculating the similarity score for retrieval. This TF-IDF model provides already a pretty good statistical approximation of role of keywords in texts. Yet one thing it doesn't take into the account, that the length of documents affects the role of these keywords in these documents. The very famous formula in informational retrieval, which you probably have heard of, makes several adjustments to this TF-IDF model, taking the length of the documents into the account. It's called Best Matching 25 or BM25, and here is how it calculates the similarity score between a query Q and document D from a corpus. It's not as scary as it looks. It's just a sum of scores that each keyword in the query has in the document D, scaled by the importance of this query keyword in the whole corpus. And we already know some components. Here is term frequency of each query keyword, which shows how many times this keyword occurs in the document D. And here is the inverse document frequency of every keyword, which shows how rare this keyword occurs in the corpus of our documents. When it comes to the rest, these parameters assure that the document's length is taken into the account. K here, for example, controls the saturation of a term frequency, and B is a parameter responsible for a scored document length normalization. It controls the influence of the disparity between the current document length and the average length of documents in this corpus. The default choice of these parameters is for K something between 1.2 and 2, and B equaling 0.75. So, to design a proper retrieval system, our previous TF-IDF representation should be updated with BM25 parameters. Now let's see how to implement BM25-based retrieval directly in Qdrant. This time, besides installing Qdrant Python's client, we are going to use FastEmbed, Qdrant's lightweight embedding library, which was already mentioned in video 1 of day 1. We are going to install Qdrant and FastEmbed integration. This integration will help us to save us some time in these steps when we will have to embed into the sparse representation our documents, index them to Qdrant, and then also do the same operation with queries when we will want to retrieve the most similar documents to these queries. And we will see how this integration actually helps with that. Besides these two libraries, all the setup that we are using in this notebook is absolutely repeating the setup we were using in the previous videos of this course. So basically, we're going to use Qdrant Cloud. And if you don't remember how to do that, everything was already shown before. Check it out. And we can dive directly into the lexical retrieval with BM25 and Qdrant and create a collection where we are going to store our documents converted to sparse representations based on BM25 formula. If you look at this step of creating a collection and you just watched the previous video, you will see that the step looks pretty much similar to what we already done, but the only difference that we are doing here when configuring our sparse vectors is switching on this IDF or inverse document frequency modifier. And let me refresh once again what's going to happen when we are going to switch that on while configuring a collection. So BM25 formula can be represented in this way, where we are dividing it into two components. One component is this inverse document frequency of a keyword, so its rarity, its importance in the whole corpus. And the rest is the function which you calculate directly on the document that you are scoring against the query. So this inverse document frequency part, which is calculated on the whole corpora, can be calculated by Qdrant when you switch on the inverse document frequency modifier. So now we configured it, it's already switched on. And since this IDF part is taken care of, so when you are going to take your documents and convert them to sparse representations, the only thing that you will have to do is to calculate on them the rest of BM25 formula. And this part is only calculated directly on the document that you're trying to convert to a sparse representation. So not much headache connected to calculations. And yet it might be a little bit non-trivial, especially if you see this formula first time and it looks very long and scary. So instead of thinking of how to do it, it can be done with fast embed. So let's see, what do I mean by that? Here we have our function, which at the same time, using fast embed and Qdrant's integration, converts our documents to sparse representations based on BM25 formula, and then absorbs them already to Qdrant. As you can see here, we are not passing anywhere indices or values as we were doing in the previous videos when we were absorting our sparse vectors. Here we're using directly texts. So in our case, we have our grocery item descriptions, and we are passing texts of these descriptions, which we are going to embed. That's exactly how using Qdrant's and fast embed integration looks like. So you're just providing in this certain way information you're wanting to convert to vectors, be it text or images, and you're providing a model you want to convert them with. So in our case, it's BM25 plus model-specific parameters, which we are going to discuss now. Let's look through implementation details. So firstly, if you remember in the formula, there was average length of all documents in the corpora. Qdrant and fast embed don't calculate that for you. So you will have to estimate this value yourself and provide as a parameter. Here we are doing it in a very simplistic way. Then the next implementation detail is that default BM25 parameters in fast embed for K and B are written here. It's 1.2 and 0.75. So here I'm just using default parameters, but of course, if you want to optimize, you can pass K and B in the same way as average length. And the third thing is how BM25 divides texts on words. Here we're using snowball stemmer, so we are dividing texts not on words but word stems, so roots of the words. And then BM25 in fast embed also filters out stop words specific for a certain language. For example, for English, it would be and or, so words which don't play a huge role in the text and don't adapt to its meaning. Therefore, BM25 and fast embed works with a limited amount of languages, which we stated here, so the ones which we have stop word lists for and the ones that Stemmer can work on. Knowing all of these details, we can run our function, which is going to calculate our average length. And at the same time, what's happening here is that fast embed locally, in our case in Google Colab, so using resources of Google Colab, will download the model. In this case, it's BM25, store and locally inference our sparse representations, and under the hood, absorb them to Qdrant. Even though it's done locally, so here it's local inference, Qdrant also provides cloud inference, if you would like to use it. Now we have everything uploaded and converted. If you would like to see how it looks, you can check out in the previous video how to access web UI and check in its sparse vectors, but we are now going to move to the next step, which is directly BM25 based retrieval in Qdrant. Suppose we're searching for the word cheese in our grocery items vocabulary. Let's break down what exactly is going to happen. In step 1, for every keyword in the query, our query is one word, cheese, fast embed will extract its stem, so it's going to become cheese. And then stem is going to be mapped by fast embed to a corresponding index that we're going to use in our sparse representation. Then on the step 2, Qdrant will look up this index in the inverted index, which we already discussed in the previous video. And it will find all the documents by this index which contain this stem of the word cheese. On the step 3, we will take our score that this keyword cheese has in this particular document, per each document, and scale it by IDF of cheese, which Qdrant separately stores. And then the final similarity score between the query and the document is going to be a sum of all the scores of all keywords from the query. So this process will repeat for every keyword that query will have. In our case, it's only one. Let's see what's going to happen. We are getting 2 scored points because out of 3 descriptions, only 2 contain the keyword cheese. And the mac and cheese one is scored higher than the grated hard cheese. It's due to the fact that BM25 implementation in fast embed considers and a stop word, so it doesn't calculate it when estimating words' importance in the documents. So cheese is considered one of the 2 words in the text, so it plays a bigger role than one of the 3 words in the text. You can see it. Here we have indices of the word cheese, here and there, and this one has a higher score than this one. As you remember, this part is BM25 formula besides the IDF modifier. And that's basically it. That's how BM25 based retrieval looks in Qdrant. Pretty easy, a lot of explanations and very little code. So now you know how to use BM25 in Qdrant, and that will come in handy when you will want to combine precision and explainability of lexical retrieval with flexibility and semantic understanding of dense retrieval in a hybrid search scenario. But before you will dive into that, let's explore an approach making keywords-based retrieval semantically aware, so sparse neural retrieval. Let's passwordify a little bit this semantically aware part. As we discussed before, bag of words sparse textual representations don't take into the account words order, so which words are surrounded by which, or words context. And the meaning of words stems from this context. For example, I want some hard-to-get cheese, and I want to get some hard cheese puts different meaning in the word cheese, even though the words in the text are the same. Sparse text retrievers, based solely on word statistics, without minding their interactions, are unable to capture keyword semantics, which, obviously, affects the relevance of the retrieved results. We are aware that a not soft cheese is closer to hard cheese than soft cheese, just by the meaning, and BM25 lacks this understanding. Sounds like a perfect task for dense retrieval. Yet keywords-based search is pretty much attractive in many domains where the preciseness is a key. Sorry for this tautology. For example, medical, legal, e-commerce, and many others. So what could be done? A common choice is to take BM25-based retrieval and apply some semantically aware reranker on top. The thing is that reranking is a pretty expensive operation, so it would be much more convenient if our retriever, which works on keywords, would be also semantically aware. Well, then what if instead of assigning weights to our keywords in our sparse representations based on some statistics calculated by a statistical model like BM25, we're going to leave it to something which we know from practice knows how to capture words' meaning in the context, to machine learning models. Then these weights will somehow also encapsulate the keyword's meaning. How? Well, Basically, authors of sparse neural retrieval take our old dense encoders as a basis and adapt them in a certain way that they produce the sparse representations similar to the ones that we saw before with BM25, but the weights are assigned by machine learning models. If you're interested in more details, you could check out this article. Probably the most famous model in the field of sparse neural retrieval is called Sparse Lexical and Expansion Model, or SPLADE. It uses bidirectional encoder representations from transformers, or BERT, as basis, and works mainly for English language. Not only SPLADE assigns weights to the keywords based on the interactions that they have in the text, but also it expands both queries and documents with semantically matching keywords. For example, encoding the query cheese, it will expand it with words like dairy, food, or dish, along with many others. And the sparse representation of mac and cheese description, which we will encode and store for the future retrieval, will be extended with the words like restaurant and a brand. This is done by SPLADE authors as an attempt to solve a so-called vocabulary mismatch problem, when two texts describing the similar items or similar concepts, as for example, Parmigiano and hard-grated cheese, have no matching words between them, which means that by a general lexical retrieval, they could never be scored as similar. Seems like a promising approach, but how to use it in practice? Well, a Qdrant and FastEmbed integration allows you to use the latest model of SPLADE family, SPLADE++, as easy as we were using it before for BM25. Let's check it out in practice. So the first step is going to be pretty similar to all the steps that we already saw working with sparse vectors, is configuring a collection to use our SPLADE+ vectors. And here, as you can see, the operation looks pretty similar to everything that we saw before. The only difference with BM25 case is that we are not configuring any IDF modifier, because SPLADE++, as all models from its family, doesn't use any statistical models to calculate words importance in the text. It assigns them based on the learned machine learning model. So after we configure the collection for SPLADE++ vectors, we can embed and absorb them in a similar way as we did it with BM25 based vectors. And here, if you look at the function, it looks pretty much identical to what we already did for BM25 formula. We're taking textual descriptions and we're selecting a model's name. And that's basically it. So under the hood, the model is going to be downloaded. Every text is going to be converted to a sparse representation and then absorted to Qdrant. What's different here? It's what exactly happening under the hood in SPLADE. And let's debunk it in a similar way we did it with BM25 formula. If FastEmbed's BM25 works on stems of words, SPLADE++ works on tokens. Tokens are a small units which text is comprised of. It can be words, it can be word stems, and it can be even sometimes letters. That depends on the tokenizer the machine learning model uses, but these tokens form a vocabulary of a machine learning model. For example, SPLADE++ operates on a fixed vocabulary of a little bit more than 30,000 tokens. So when our text is broken on tokens, SPLADE++ models can map it to indices in its vocabulary and operate on these indices directly. The same indices are going to be used in our sparse representation. If you would like to check out how this tokenization and conversion to indices work, you can go to Tokenizer Playground Hugging Face, and here select a custom tokenizer and put the name of the model you're using. And here you can work with different texts. For example, if our document is mac and cheese, you can see how SPLADE tokenizer converts this text to token IDs or directly to tokens. Here is 3 tokens, mac and cheese, and here are their IDs. For example, cheese has ID 8808. Now SPLADE++ model already can understand text per se because now it's converted to readable to SPLADE++ indices mapping to words in SPLADE's vocabulary. Then SPLADE will process all of these mapped representations and assign each token a weight based on the importance that SPLADE thinks this token is having in this document. And simultaneously, SPLADE or SPLADE++, I'm using it interchangeably here, will expand our documents and our queries with tokens which SPLADE once again thinks is contextually relevant to this document. For example, for mac and cheese, it will be additionally around 15 tokens and non-zero weights with their importance added to them. If you would like to experiment with SPLADE expansion behavior, we have a separate tutorial on how to work with SPLADE in FastEmbed, and this tutorial provides the function, and this utility function allows you to map back the sparse representations produced by SPLADE++ to tokens and their weights. So you can see what exactly SPLADE++ judges as contextually relevant for every document, and also actually a query. So here happens the same thing as was happening for BM25. FastEmbed downloads SPLADE++ model and uses Google Colab resources to convert our text to sparse representations and upload them to Qdrant. Now we can check out this sparse neural retrieval, what it does bring to the table compared to the classical lexical retrieval. And let's start with an example which I used in the video before, that the query a notes of cheese will be judged by sparse neural retrieval far closer, much closer to a document called grated hard cheese, because it's semantically similar things. And as you can see, it's exactly what happens. This document is ranked as the best match. And here we can actually see our cheese index, and we can also find the corresponding weight of it. All the other indices that you see here is the result of SPLADE's inner document expansion. And if we will compare it to BM25, we will see that BM25 doesn't understand the semantics behind the query, and that's why it's going to match mac and cheese higher. As we discussed before, cheese has a bigger statistical role in this text from the perspective of BM25. So that's how sparse neural retrieval can win over lexical retrieval in certain use cases. And also, if you noticed, here SPLADE, providing the answer to the query a notes of cheese, also found for us a white crusty bread roll document, which is absolutely impossible to match with BM25. And that's due to SPLADE's inner document and query expansion that we already discussed. And this expansion mechanism is there to solve vocabulary mismatch problem. So for example, as I was talking before, if you will try to match Parmesan with grated cheese, SPLADE, by innerly expanding both query and the document with additional keywords, will expand them with matching keywords, since they are contextually relevant to the document and the query, and this will allow to match both document and the query. With BM25, it's impossible. So sparse neural retrieval can be a game changer. Now the question is whether SPLADE models are the one and only ideal option to use for sparse neural retrieval. They are certainly a strong choice, and yet they have their limitations. Firstly, using tokens instead of words or stems in informational retrieval is not very convenient, as many words are broken into the meaningless pieces. Secondly, document and query expansion mechanisms used by SPLADE not only make the resulting representations less sparse and inference more heavy, but also they make results sometimes pretty far less explainable. For example, as in the case where mac and cheese description was expanded by SPLADE with the token apple. Knowing these limitations, we have an ambition to expand your choice of sparse neural retrievals, and in general would like to push this field forward, fostering the adoption of lightweight, explainable, and usable sparse neural retrievals. We have trained and open-sourced a couple of them, the last one being minicoil. You could use it in FastEmbed in a similar way I demonstrated you of using BM25 and SPLADE++ with Qdrant and FastEmbed. In general, when choosing a sparse retrieval, lexical or neural, what you should do is to experiment and find the best choice for your specific use case and for your data. And when you find it, you already know how to use it in Qdrant. However, sparse, even neural, retrieval has its limits. It's not so ideal when you need to match between something which is expressed in a very different way, but semantically similar. This is a perfect job for a dense retriever. So on one side, we have our sparse retrieval, which is explainable, lightweight, and precise. On the other hand, we have our dense retrieval, which is perfect for exploration and naturally bridging this vocabulary mismatch gap. Well, then why not have both? You will learn how to combine them in the next videos about hybrid search, which are going to be done by my colleague. And I'm leaving you in his hands.